Hi, I'm Barbara Fox, and I thought today I would make a video about traffic services. Basically, how traffic comes into a router or switch and traverses that system and then egresses the switch. So, really talking about traffic services within the switch itself. So, when traffic comes in from a customer, it enters an ingress port and it's classified basically to identify individual flows, individual customer flows. And we look at the frames or the packets, we look at the priority fields within those frames, and we tag them with an internal COS, an internal cost. And that is how that packet will be treated within the system. It might only have a cost value, it might have a cost value and a color. Then what we do is we police the traffic based on the contract that the customer has with us. So we make sure that the amount of traffic that they're sending into the network doesn't exceed the contract that we have with them. After the traffic is policed, it's forwarded to a virtual router or forwarder. So if it's layer 2 traffic, it'll go to a virtual switch. If it's layer 3 traffic, it'll go to a VRF. And that forwarder will determine what the egress flow point is to egress the system. Now, at the egress, there'll be queues associated with the flow point. And the way that a packet will determine which queue the packet should be enqueued to is based on that internal COS. All right. So we'll look at the internal costs and determine which queue that frame should be queued to. Then what we do when we have these queues in the queue group is we shape them. Basically, it's almost like the metering on the way in. We're making sure that we're not sending out more traffic into the network than the network can handle. And so we'll do some congestion avoidance if there's too much traffic. And we'll talk about that a little bit later. Then what we'll do is we'll remark the COS in the frame based on the ICOS. So we'll send the frame into the network with the right costs for this flow. And then we'll schedule the traffic out the port, which will determine which packet should be taken off which queues in which order and forwarded out onto the network. So the first thing that we're going to do is we're going to classify the traffic to an ingress flow point. So classifications are saying, okay, we're receiving traffic on this physical port. What flow is this packet? To which flow does this packet belong? So it might be a layer 2 packet. We might look to see whether or not it's untagged. If it's tagged, is it a single tag? Is it double tagged? We might try to determine if the layer 2 control traffic is part of a flow. We can look at the priority information in the packets themselves and use that as part of the determination. Or we may look at layer 3 information. What's the destination IP address? Or we might look at an MPLS tag and figure it out that way. So the next thing that we do is we look at the priority information in the frames or packets that are being received to determine what we're going to use for an internal cost for these packets. So if it's a Ethernet packet with a VLAN, we look in the VLAN header and there's 3 bits of PCP. So values from 0 to 7, and that's our priority. And then there's a DEI bit, which is a discard eligibility indicator. Basically, if that's turned on, then this packet is eligible to be thrown away. It's considered yellow traffic. If it's off, then it's guaranteed to go through the network, to the best of our ability. So if the DEI bit is set to 0, it's not really eligible to be thrown away, and it's considered green traffic. If we're receiving MPLS packets, then we look at the experimental bits. Again, it's 0 to 7. And this is really the priority of this MPLS frame. If we're receiving IP packets, if we're looking at the IP headers, there's a DSCP field in both IPv4 and IPv6 headers, and that's a value from 0 to 63 that defines a per hop behavior, which defines how these packets should be treated relative to other packets in the system. Okay, so we'll look at these values and then we'll assign an internal cost, maybe an internal color as well, to each frame that we receive. And so here we're showing you, these are some of the cost values. This would be a PCP value, and this is the internal cost that we're assigning to each frame. It'll be tagged. And then here, we're showing how it'll be remarked on the way out, what value will be put into the packet, into the PCP or the MPLS experimental bits in these cases on the way out, and the color. Okay. So the next thing that we're going to do is police. So we use CIR, EIR, CBS, and EBS. So CIR is a committed information rate. It's basically how much traffic we've guaranteed to the customer. And so they're probably not sending, at a constant CIR rate. So occasionally they might need to burst up to send more traffic. The traffic might be a little bit choppy. And so in that case, we have an excess information rate, how much more traffic will send in beyond their EIR, beyond their CIR value. And the burst size is really how much traffic we'll send at once. We can do hierarchical policing as well. So basically, hierarchy lets you see further into the network. So here we've got a router, and the router is connected to probably a router in, maybe one of these buildings. And then that router might have connections to individual offices within this building. And so hierarchy lets you look deeper and deeper into the network. So in this case, maybe we have 3 gig of CIR that we allow this entire building to send. So its parent scheduler would be 3 gig. And then maybe individual offices would have 1 gig, say. So say there were 3 offices in here and each of them had a CIR of 1 gig. They would each have a CIR of 1 gig. Their parent would have a CIR of 3 gig. This guy probably has a CIR of 10 gig. And so you're doing hierarchical policing. Now, you could do that, or you could just police, you could have a router at this building that basically did the policing there, so you didn't really have to worry about it. So hierarchical policing is good. A lot of times if you're not bringing in IP, right, if you're bringing in something that isn't really going to do policing for you, you might want to do hierarchical policing. But other than that, you probably want to push the policing out further in the network, and so you don't have to do so much hierarchy here. All right, so now the packets have come in. They've been tagged based on their QoS information, class of service information. They've been policed, they've gone through a forwarding domain, and now they're going to an egress port. Now, an egress flow will have a queue group associated with it. And this queue group, the way that we'll decide which queue in the queue group a particular frame should be in queue to is based on the internal COS that we've marked on that frame. Okay, so we'll look at the internal COS and determine which queue the traffic should be in queue to. And in this case, I'm saying that 0 is the lowest priority and 7 is the highest priority. I've got 8 queues here. Now, each queue will have its own CIR and EIR. Each queue in the queue group will have a congestion avoidance profile. And we also have shaper compensation that's applied to the queue group as a whole. So we're going to do kind of the way that we did policing on ingress. We're going to really do policing and shaping on egress too. Okay, so I'm going to explain a little bit more about that. And then what the port scheduler is going to do is these queue groups are going to, you could again have hierarchical queuing here, although again, you might not want that level of detail. You might only want to have one queue group and you forward and you enqueue everything onto the same queue group. because you've tagged it, so you know which you might put different types of traffic on different different queues in the queue group, and then it'll be forwarded to the schedule, and we'll go through the scheduling algorithms. Okay, so the first thing in the queue group is that we're going to do is congestion avoidance. So basically, when there's too much traffic in the network, we really need the network to sort of slow down. And flows are usually end-to-end TCP, right? So the source talks to the destination, usually with TCP. And TCP has got a congestion avoidance capability where if you throw away packets, the source will start to slow down the rate at which it's sending packets, right? Because it wants the network to reach an equilibrium. So it'll start sending fewer packets, and then it'll slowly increase the number of packets that it's sending until more packets get thrown away, and it'll back off again. So it's trying to reach an equilibrium about how much traffic it can send. And so what we want to do is we kind of want to randomly throw away packets because we want a number of TCP flows to back off when we have congestion in the network. So the way that we do that is with weighted RED, weighted random early discard. And so I'm going to speak to this picture. There are values here that I'm not endorsing. I don't really know what the right values would be for your network, but I'm just going to speak to the values that are in this picture. So I told you that we have green traffic and we've got yellow traffic, right? The green traffic, we're pretty much guaranteeing that we're forwarding, and the yellow traffic is eligible for discard. So here we've got two curves. We've got one curve for the green traffic, one curve for the yellow traffic. And what this is saying is that when the queue gets 48% full, we're going to start randomly throwing away packets. And we're going to throw them away up to a rate of 4 out of every 10 packets we'll throw away. And when the queue depth reaches 96%, we'll just throw away everything until the queue is drained a little bit. We don't have to throw away so much traffic. So these are the values we're using for the green curve. For the yellow curve, we're going to start throwing away traffic earlier. We're going to start when the queue hits 24% full. When it hits 72% full, we're going to throw away all yellow traffic, and we're going to throw away traffic between 24 and 72 at a rate of 6 out of every 10 packets. Okay, so that's the congestion avoidance algorithm that we're going to apply when we're running weighted RED. And shaper compensation is for when we're doing bandwidth management. It's really the difference in the number of bytes in the header between when the packet ingresses and when it egresses the system. So if you have a frame and you're adding a bunch of headers, then you're going to add bytes of shaper compensation. If maybe it's coming in from the network and you're taking bytes out of the header, it might be a negative number. So shaper compensation is really about the difference in the size of the header between ingress and egress. Okay, so now we've queued the frame, we've done congestion avoidance, so now we know that this is the traffic that we expect to go out on the egress link. And this is where we're going to do the remarking. We're going to look at the internal QoS, and we're going to mark the frame for egress. Okay, and now we're going to schedule the traffic. So there's amount of traffic that we're going to send, and again, it's got CIR, EIR, CBS, EBS for the egress port. And instead of calling them queues, we're going to call them tap points because they're the final physical queue before we egress. And we're going to run a scheduling algorithm on these tap points. We'll talk about the different algorithms. Each tap point is going to get a priority and a wait. We'll talk about that as well. All right, so there are 4 common scheduling algorithms: strict priority, round robin, weighted round robin, and weighted fair queuing. So strict priority is that you send the highest priority traffic out first, always. So in this case, we would send, assuming 7's highest priority and 0's lowest priority, we'd send all 3 red packets, and we'd send the 2 yellow packets. And then say another red packet came in before we serviced the 3rd packet, the blue packets on with priority 5. We'd send the newly received red packet that was on Q7, and then we'd service port 5, port 3, port 0. So you're always going to send whichever frame is on the highest priority, always. That's what strict priority is. Round robin is, I'm going to take one packet from this queue, one packet from this queue, so it would go this packet, 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 this packet. So we go 7, 6, 5, 3, 0, 7, 6, 5, 3, 0, 7, 3. That would be how the traffic would be dequeued and sent out on the link in a round robin system. Weighted round robin is, instead of just taking one packet from every queue, you can say how many packets you're going to take from a particular queue. That would be the weight. So say we gave queue 7, and I should be saying tap point, but I'm going to just continue to call them queues. 7, 2, 6, 2, and then say we said 5, 4, 3, 2, 1, 0, all got 1. So we would send this packet and this packet 2, this packet and this packet. So 7, 7, 6, 6, then 5, 3, 0, then 7, 5, 3, 0, then 3. Right, so we're just saying how many packets we're going to dequeue at once. And that's weighted round robin. Now, weighted fair queuing is a little bit different. Instead of talking about just packets, what we're talking about is the number of bytes that we're going to dequeue at once and forward. So you could give different queues different weights. But let's say that we gave every queue 250. So Q7, we'll say, I'm sorry, yeah, 256. Okay, so we'll say Q7, 256, we can send out these 2 packets. They fit within 120, 256. So we'd send out red, red. Then Q6, yes, red, red. Q5, we'd send this one, but we say, oh, if we take 128 isn't enough to send 1280. So we'll save the 128 for later. The same happens on 3. When we can send 128, but we don't have enough bytes in our deficit to send this 1280 byte packet. And on Q0, 128, 256, we don't have enough to send any packets. So this has a 256 left over. These each have 128 left over. So our next time through, we say 256, oh, I'll send this one. That fits. There's nothing here to send. And now on this one, I say, okay, I had 128 left over. I add 256. This still doesn't add up to 1280, so I still can't send this packet. And so basically, we keep doing that. The first one that will go out will be this one because it didn't already use its 128. And then this one will go, this one will go. So what weighted fair queuing is doing is really just saying how many bytes can go out instead of how many packets can go out. And you just keep track of what the deficit is until you have enough bytes to send the next packet. Okay? Sometimes we don't run just one scheduling algorithm. What we often do is we'll mix strict priority with weighted fair queuing. So we might say that we're going to run Q7, 6, and 5 as strict priority, and we're going to run 4, 3, 2, 1, and 0 with weighted fair queuing. And we might give them different weights. So we might say, okay, we're going to run 7, 6, and 5 as strict priority, and we're going to run 3 with a weight of 1280, okay? And we're going to run Q0 with a weight of 512 or whatever, 640, I guess we'll say 640. So what we would do is we would send all the traffic from 7, all the traffic from 6, all the traffic from 5. Now this guy had a weight of 640, no, we said 1280. So he would send his first packet, and 1280 still isn't enough to send the second packet. So We'd wait for the next round. 1280 is enough to send, oh, this one was 640, so we don't have enough here either. The next time through, 1280, we can send this one, and he still has a deficit of 128 that he can use. And actually, whatever, 1280 minus 128 that he can use. And 640 and 640 is 1280, so we can send this packet. And then we just continue to go through. Anything new that came in on these packets would go out immediately, and these guys would run weighted fair queuing when all of these queues were drained. Okay, so that's common, right? It's common to run strict priority for some traffic and weighted round robin for other traffic. So I'm just going to show you, this is an example of setting up what you want those algorithms to do. So we've got different types of traffic, and we're going to treat it in different ways. And so we've got our packet class, what we're going to send it, the color. So this is what we're going to remarket to from the queue. Remarket to this. This is the color that we're going to use. So green and yellow. And then what we're going to do is we're running 7, 6, 5, and 4 in strict priority, and 3, 2, 1, 0 in weighted fair queuing. Right now, these guys are running these. This is our congestion avoidance. The strict priorities, we're not running any any WRED algorithm on them, weighted WRED algorithms on them. And on the lower, on the queues that are running weighted fair queuing, we don't have any green curve. Everything's set to 100%, so we're not throwing away any of the green traffic. With the yellow traffic, when we hit 25% to 75%, we're not, I don't know what the value is that we're throwing away. It's not 100%, but between 25% and 75%, we're going to send away, we're going to throw away some portion of the traffic. And then at 75%, we'll throw away 100% of it. This is not a good value, but that's okay. So, and then these are the weights that we're using for our weighted fair queuing. These are the weights that we're using. So we're saying that tap point 3 has a weight of 46, 2, 33, 1 has 21, and 0 has 1. And we've given CIR and EIR to the rest of the traffic. And these guys are really running off the excess information, right? So basically, if there's none of this traffic going through, that's when we're going to send this other traffic, okay? The premium data will go through at a smaller rate. So this would really be used to configure all of that information in your network. So I hope that was helpful. So thanks for your attention, and I hope you stay safe and be well. Thank you.